lectures left because next Wednesday is the exam. So I'm not going to start anything new that I would expect you to know for the exam. But I thought today I'd just give you a sort of a lecture on a topic that has been of great interest to me and to the community in algorithms for, at this point, 20 years or so. But it's, even though it's been around for 20 years, it's not something you would ever typically encounter in an algorithms class. And so it's just a fun thing that I want to share with you. And then the next two lectures, I'm thinking we'll do some kind of review where I'll go over different components of the material we covered with an emphasis on thinking about, okay, how do we, what are the things, just review the topics. Also, how do you reason about correctness and other things in those domains, right? So for a randomized algorithm, for a dividing counter, things you may have forgotten, just go over that again. So that when you have to do your final exam, you sort of have some, you can refresh this a little bit. So that's the plan, okay? So today we'll do streaming algorithms, and then Friday and Monday we'll do review, and then Wednesday is the actual exam, okay? All right. So this area of what is called streaming algorithms it started. The first paper on this came out in 1997 or so. So it's been about 22 years. But it's this very radically different way of thinking about algorithm design that people have never really thought about. Well, they kind of had, but hadn't at the same time thought about before. And in the realm of sort of big data, this has become a very important way to think about how we design algorithms. And in fact, many of the ideas that come about from studying streaming algorithms have been used in places where you don't even need to stream, just because they're very efficient. So what is the particular challenge you're dealing with here? So the challenge you're dealing with here is, well, you have lots of data. So all of our algorithm design has worked under the assumption that if I want a piece of information, it's sitting in memory somewhere, I can get it. Right? So a very basic assumption. We write our code, we analyze the code, we assume we have to look up an array element, it's there. It takes constant time to look it up, or whatever it takes to look it up. We never worry about the fact that actual machines, things take time. You may have a cache, you may have two caches, you may have stuff on disk. And the time it takes to access something depends on where in your memory architecture it is. You can't just assume it takes the same time. And this is a problem because, as you probably have encountered before, if you have lots of data and it's actually sitting on disk, and you have to do something even innocuous like sorting, it'll take forever if your data is sitting on disk. It'll take much longer than it would take if the same amount of data was sitting in main memory. So it's not even just the amount, it's that it's in a different memory system altogether. And of course, if you have, let's say a terabyte of data, there are very few machines that have a terabyte of RAM. So if you have a terabyte of data, it's going to be sitting on disk and you have to sort it. How will you do that? So this idea of thinking through algorithm design with another kind of abstraction in mind. So rather than thinking of I have the CPU and I have memory and I can access anything I want, people said, okay, in order to model the fact that disk access is so much more expensive than accessing memory, we should come up with a different model of computation. A model of computation that reflects this fact. And so the model of computation we came up with, and this was back in the first version of this came up in 1988 or so, was something like this, where you said, okay, there's CPU, and there's memory, and all of this is in a block. And then there's your disk. Okay? And whenever I implement an algorithm, the only thing I'm going to charge you for is when you access something from disk. I'm not going to charge you for anything else. Now, this is of course silly. Algorithms take time to run. Even if all your data is in memory, it's going to take some time to run. Why would you do this? Well, you do this because, and I don't know what the current numbers are, but for many years, the discrepancy between accessing a byte on disk versus accessing in main memory, whether it's an L1, L2 cache, or even in your main memory system, was something like a factor of 1,000. It takes that much longer to access something on a disk. And it's even worse if the disk is somewhere further away. If it's a local disk, maybe it's one thing. And so the idea was, okay, if you're comparing a cost of 1,000 versus a cost of 1, you might as well not worry about the cost of 1. You might as well only focus on the cost of 1,000. So if this is 1,000 cost, 1 unit of access here, so this takes 1 unit this takes 1 over 1,000th of a unit. So you might as well ignore it. We're also not calculating the time it takes to add, subtract, divide, do all the other things you do in a program. It's an approximation to the model, but it's a model that tries to focus your attention on what's most important, namely the disk axis. So in other words, designing a model of computation is not an attempt to be realistic. It's an attempt to say, where's the choke point in my algorithm design process? And if I had to design to worry about that, what do my algorithms look like? And so what you find typically is that when you do this, it's not like I'm saying, okay, if I design an algorithm that runs in 1,000 units of time, that's a representative of how long it's going to take. It's more like if I have one that takes 1,000 units of time and one that takes 500, that ordering will be the same if I implement it, right? So a lot of algorithm design work, we're not looking at the specific time it takes, but we're looking at relative. If I have two different algorithms, how do I compare how well they're going to do? So this had to be modified a little bit because, of course, you don't get access from disk in one byte at a time. You get access in blocks, right? So the what is called the disk access model, or the external memory model, had two components. So there was a main memory, and it's at size n. There was a disk, which is essentially infinite in size. You can have store whatever you want. And every time you made a request to disk, you would pull in B units of memory at a time, one block. And for different machines, you might have different specifications of the block sizes, or you could even customize it. And so what you were counting is if you had to implement an algorithm, how long would it take, how many disk accesses would you need under the assumption that each disk access got you B units of disk. And of course, you would assume, again, the data was sitting on disk. You wouldn't be able to make any assumptions about how it was sitting on disk unless you did the work to relay it out, which would again cost you. And so, of course, the most basic question you could ask is, can you sort? So now we know that sorting n items takes n log n time. And you could put everything on disk and implement your merge sort, it would just sort everything. But that would be very bad because you'd be spending essentially a lot of disk accesses to get everything in. And your running time would, if you didn't do anything cleverly, would be basically, if you have n sort n items, would take n log base 2 of n time. Right? This is what you'd expect. But this would be the number of disk accesses, the number of IOs you need. That would be very bad. And the question could, well, we don't know if it's bad yet, but the question could be, could you do anything better than this? If you think about it now, the fact that you can extract B units of memory at one time suggests that your real effective input size is not n, it's n over b. Because in n over b disk accesses, you can read the entire input. Just like with n accesses in main memory, you can read the entire input. So the real input size is n over b. So we would like n over b log base 2 of n over b. And maybe there's a way to design it. I don't know yet, but maybe there's a way to do that. But it turns out that you can actually do even better than that. And one way to think about this is that if I want to implement merge sort, what I should do is pack as many things into my main memory as possible, sort them, push them out, and then do this again. Right? So you need something like m over b IO accesses to get things into main memory, do things and sort them and push them out. And it's not, basically, I won't get into details here, but there's a version of merge sort you can implement in external memory. So one of the first algorithms that people came up with, which takes n over b log of n over b, but the base of the log is not 2. The base is much higher, which means the runtime is much smaller, and the base of the log is m over b. Essentially, you can create a very high, so merge sort you can think of as having a fan out of 2. You take 2 streams, put them together. In merge sort in external memory, you don't want to take 2 at a time, you want to take as many streams as you can as a time. So it turns out you can do like an m over b way fan out and do merge sort simultaneously in main memory. Remember, it's not what we do in main memory doesn't cost us anything. So we can do what we want and we can. And you could show that this is in fact under a comparison model. As usual, this is the optimal number of IOs you need. You can't do any better. So this led to a lot of study of how you can design algorithms that work efficiently in external memory. And what's not surprising to you probably is that the best kinds of algorithms, what they end up doing is scanning the disk, copying a whole bunch of stuff into memory, doing something clever with it, pushing it out in a sequential scan, scanning a whole bunch of more stuff into memory, doing some stuff with it, pushing it out. And very rarely would they get like small pieces of information on disk. Now, if you didn't know anything about this model, and I asked you to go and implement something on a disk, after a while of trying out, you would probably come up with the same thing yourself. Right? If you ever done anything with disk, you realize that you really can't do things like do a bunch of random accesses. You want to sort of pull everything into main memory as much as possible, and then do something and throw it out. So in some sense, while the model may not be telling you anything you couldn't have figured out yourself, the fact that the model exists and the fact that it says what is optimal in this model essentially changes the way you think of your design to be the way you actually should be doing it. Right? So the algorithms that are optimal in this model tend to be algorithms that implement well, even though the model itself is somewhat unrealistic in ignoring how much things cost you. So one of the important things that maybe we didn't talk about enough in this class, that algorithm design is not just about space and time. It's about resource management. I give you a resource, it's an expensive resource, and I want to use as little of that resource as possible. We've seen that with time and space, of course. We've to some extent seen that with randomness. We want to use a little bit of randomness and improve our behavior. And now I'm showing an example where the resource is merely access to disk. And the algorithmic question is, how do you minimize the use of this resource? And so over the past 20 years, we've come up with many different models to focus on different aspects of resource usage, whether it's space, time, communication, right, and different nodes in a distributed system, and then design algorithms in those models that, even though the model is not realistic, the algorithms you come up with tend to do the right thing. And that's the value of doing this kind of model. Okay, so the external memory model came up and people studied for a while. And then people said, well, why stop with just external memory? You also have a hierarchy within your memory structure. For example, you have a cache. A cache gives you very quick access, much quicker access than access to main memory. Okay, so you could imagine that instead of having a two-level structure, you have a cache, and you have memory, and then you have disk. And in each case, maybe there's a 100 factor here, then maybe 1,000 factor here. So again, you want to design your algorithms to be respectful or to be cognizant of the fact that storing things in your cache is great, but of course cache is small. Storing things in memory is great, but of course memory is small. Storing things in disk, well, you can store what you want, but it takes longer. So now you get a sort of a hierarchy, and this could, you could imagine multiple little hierarchies. And so, people studied this for a while, and they said, well, maybe I don't want to design my algorithm to be so specific to a particular architecture. Maybe I want something that will work correctly or work optimally, regardless of the relative sizes of cache, main memory, and disk. Somewhat automatically auto-tunes itself to work. And so this led to this idea of what are called cache-ability algorithms, which again has been a sort of a, I won't talk about this here because we're going to talk about streaming next, but there's been a sort of an area of study. In fact, I know some folks who actually built sort of successful companies around building cache-ability data structures for doing database management. They sell their software to various companies. But all of this comes from this basic idea of, if I change the way I think about resource usage and change my model of resource usage, how do I design efficient algorithms? And all of this has been driven by big data work, right? To those data and the culmination of this, at least in my mind, the culmination of this whole story is in this idea of a streaming algorithm. And so let me talk about it. And I don't know if any of you have heard of streaming algorithms. You may have. This is one of those things that's so successful, no one's heard of it. People use streaming algorithm technology all the time without realizing that this is where it came from. What's a streaming algorithm? A streaming algorithm takes this idea to its extreme scenario. And it says, imagine that I have a huge fire hose of data coming in. Really big fire hose. So you think of standing there, the data's coming at you. All you can do is pick out little bits and pieces of it and store it. but you can't actually store the file. It's too big. Okay. There are a couple of examples I can give you. One example is if you're sitting on a router. If you're sitting on a router at the edge of a network, and you're maybe a smart router, you're doing some SDN stuff, you have packets just coming at you all the time. Okay? Your router is small, it has maybe some memory storage, but not a lot. Maybe it has a few gigs, that's nothing compared to 100 packets coming. You can't store all the packets coming, but you want to do some computation on the packets coming. So that's one example. Another example, since we're talking about astronomy nowadays with the black hole stuff, is there is this thing called a Sloan Visual Survey, right? There's a bunch of basic telescopes all over the place, all of outside the planet as well as on the planet, getting all kinds of streams of information in at different wavelengths, right? Different kinds of information. Some are X-rays, some are gamma rays, some are this, all coming in. And I don't know the exact number, but we're talking about literally terabytes per minute kind of data coming in, just from these imaging methodologies. Now you don't know ahead of time what information you want, and you can't store this, not realistically. There's just too much of it coming in. So again, you have to find some way to make sense of the data and store some aggregates very quickly as the data is going by, and then it's gone. So you get one shot at the data. It comes, you get a shot at it, you can copy little bits and pieces of it or some modifications of it, whatever you feel like, and then it's gone. And now the question is, what can you compare with this? So let's come up with a model. So this is what's called a streaming model. And again, the idea is that you have a stream of data coming by. Okay, so think of it that way. And I have a machine that's kind of listening in as the data comes by. Okay, think of it as a network of lines. And the machine itself has access to some small amount of storage. Right, in main memory, whatever. I don't really know. There's some small amount of storage. And it can store whatever it wants from the input. It can store the input raw, it can process it, it can do, I don't care what, anything it wants. The limit being that all it has access to is this tiny amount of memory. So all it can remember is a small amount of stuff. And it has to compute something. So let's be very concrete. Let's say that let's say the input consists of items A1 through AN. You can think of these as numbers if you want, or something more complicated, it doesn't matter, where n of them coming in. And my memory of this machine that's listening in is much smaller than n, so smaller than n. So think of it like square root of n, or log n, or log of n, like really, really small. Okay? And now, I want to do something. This is my computational model. I can do whatever I like, but my constraint is that I have only this much memory. Does the model make sense? This is what's called a streaming algorithm model. And the data just comes by in one shot. I don't get to see it again, right? I can't just keep reading it. Otherwise, I could maybe do something better. But no, it's just come and goes gone. Does the model make sense? Yeah? So let's start very, very simple. How much memory do you need to figure out how many items there were in the string? If I want to count the number of elements in the string, how much memory will I need? And what will be my algorithm to do it? What do I do? I want to know what n is. So am I coming in? I'm just waiting for that. I want to know how many there are. How much memory do I need? And can I do this? Sorry? Constant, like 2?
Like maybe if we can keep a count, just a single.
Okay, how many bits do I need to keep a count of all the items in my string? Yes, it does, but what is it? I have n items in my string. Sorry? I need log n bits. Right? To count anything. And what is my algorithm? Well, that item comes, I increment the counter. Right? It's very simple, right? Okay. So I can count elements in log n space. Can I do better? Can I use less than log n space? This is my resource now. Can I use less than log n space?
I
Yeah?
have a doubt. So
Yeah.
this square, the bigger square.
That's the machine.
That's
That's
the
the machine. Yeah.
So it has the algorithm, or right now it's just filtering data.
It has whatever algorithm you want to implement.
And then finally the filtered data goes into the.
There's no filter data. There's just arbitrary amounts of memory that can store whatever you want. It could be filtered data. It could be some computation of the data. It could be anything. In this case, it's a counter. So can I do better than logging?
You can probably trade space with precision, so you can count every 100, and then you will be storing decimal numbers.
Right. So it turns out that so I said the first algorithm on streaming came out in 1997 in the era of big data. The first paper that suggests how to count in less than log-n space came out in 1977. It wasn't so much an issue of big data, but small memory. Computers at the time had very few registers, and the question was, can you count using very few registers? And in fact, it turns out that you can do this. If you're willing to say, I will produce a number, k, which is in the range of 1 minus epsilon times n to 1 plus epsilon times n. And so epsilon is my tuning parameter, as always. I want to approximate the value n, and I'm allowed to output some number in the range. You can do this. Essentially, the idea, roughly speaking, the idea is rather than counting what n is, you count what log n is. And since to count log n, you need log of log n bits. That's the number of bits you need. But because you're counting log n and not n, there's going to be some errors. And as long as you can make sure the error in counting log n is small, that will transmit to a multiplicative error in counting n itself, roughly speaking. So this was back in 1977. It's kind of interesting because it was well before we were worrying about these things. So let's think of another problem. Suppose that this is a very common problem. I want to do, say, top k counting, right? I want to compute sort of most frequent items in a set. So let's make this even simpler. I have a bunch of items. My input consists of a bunch of items where AI is drawn from some universe, and the universe is of size m. So the stream is of length n, the universe is of size m. Find so these could be, you're tracking IP addresses and you want to figure out where some of the source traffic, where most of the source traffic is coming from, the most frequent source of traffic. Right? There could be other reasons you want to do this. But now we're in a streaming model. Right? You can think of n and m as both very big numbers. Right? If you have IP addresses, for example, you have terabytes of IP addresses, but of course you have 64 bits, so that m is 2 to the 64. It's a very big number. Can you do this? So again, this is now a puzzle. I've given you a model of computation. I've given you a question. If you had a regular model of computation, just normal RAM model, the computer model, this is trivial. Sort them, you do whatever you want, right? Get the problem. That's easy. In this model, though, the data is just whizzing by you. Can you do this? I want to find the most frequently occurring item. Not even the top 8, just the top 1. So think about this for a few minutes and think about where the challenge is. By the way, remember you don't need to sort, you can do it faster than that. Not many times. So any thoughts so far on where things are looking difficult? Where the challenge is coming from? very stuck. So maybe one way to think about this is, how would you do this in deep memory in linear time? What would you do? So my only constraint is time. I don't know what anything else. Well, how would I solve this problem? Find them. I give you a bunch of numbers. They're somewhere lying around. Find the most frequent. What do you do? Come on, this is not a grad algorithm's question. Right? So what would you do?
Maybe the count of each each item.
Yeah.
Then
Okay,
if
good.
there's repetition, you keep increasing.
Okay, good. So how much time will this take?
I mean, paper size.
So n. How much space do you need? How many counters do you need?
That depends. Yeah. So maximum n. I mean, at least for the
N or well, is it n or m?
input stream.
The length of the input stream is n,
Yeah.
but the number of counters you need is what? It's a number of different types of objects, which is n.
N.
So you need n memory, just make it compact. Okay, so that's not going to work. I'm not allowed to have that much memory. What's another thing you could do? What is the way we learned in this class of how to, reduce the size of the input we want to process? What is one trick that we've learned? What is the trick we learned to reduce the size of the input? We learned this in class, right? That instead of processing the whole input, we can do something better. Hashing. Okay. Can you say more?
So we can keep set of buckets based upon the accuracy we want.
Yeah.
So as we read each and every input, we just completely hash different hash values in different buckets.
Okay. So now what do you do? So now you get a bucket and you can say, okay, this bucket has the most number of items. Right?
Yeah. So when you raise up the hash values, the elements you can rent are the most frequent.
But which is the most frequent element?
So we will have the set of elements as frequent. We cannot put one most frequent.
Good. So let's say we want to use memory that's small. So let's say the number of hash buckets we're willing to tolerate is something like k. Okay, we have k hash buckets. We generate a hash function. We probably do some random, but that's fine. And then we hash everything, right? So now we look at the different hash buckets, and we look at which bucket has the most number of elements in it, right? We hope that because we've chosen the hash function at random, that every bucket represents roughly the same number of elements. This is slightly off, but probably some 1/kth fraction of the universe is going into one bucket. Right? So now this bucket is maybe the biggest bucket. So we say whichever elements were mapped with this bucket, somewhere among them is the most frequent element. Or somewhere among them is the element that has the largest frequency in order to report the frequency, let's say. The problem now is that if you set k to something small, let's say k is something like, let's say square root of n, because we want something to be much smaller. Okay. Then on average, you could have something like square root of m log n elements hashed to this bucket. You'd want square root of n perfectly, but there might be some noise because of randomness, so it's like this. Okay? And each of them might be very infrequent, but because there's square root m of them, that bucket wins. Right? So that means that your reporting of, okay, some element here is the most frequent element could be completely wrong because there could be one element hashed to this bucket, which has as much count as this, maybe off by 1. But now the element you report has a frequency that could be of 1/√m times the actual frequency element. So the maximum frequency element could have frequency f, but the element you report a frequency f over square root of n. So there's a huge gap, and that gap is precisely controlled by the number of hash pockets you have. But in order to make this better, you need to increase the number of hash pockets to basically almost n. Otherwise, you're never going to get a good estimate. In fact, it turns out that this problem cannot be solved. You cannot get a reasonable approximation to the most frequent item in a stream. This is one of those problems that is very hard for a streaming algorithm to solve. You can get like within a factor 2 with a bit of work, along the lines of what you submitted a bit more cleverly with some hashing, you can do this. But this is actually a hard problem. You need to be able to give up getting an exact answer. You need to be able to give up getting an answer reliably, so it has to be randomized. And even then, you're within a factor of 2 or 3, I think, for the right answer. So getting top k elements is very hard. Okay, unless they're sufficient. So this is an example where the streaming model makes a problem that would seem very easy suddenly very difficult. So I showed you a problem that's easy to solve, counting the number of elements. I showed you a problem that's very hard to solve, counting the most frequent element. Let me now introduce a new problem, which seems like, well, I don't know what it seems like. So what I mean by this is that if my input consists of the numbers 1, 2, 7, 1, 3, 4, 7, 3, 7, 2, 1, right? The number of distinct elements is 1, 2, 3, 4, 5. So the number of distinct elements but even though the stream length okay, and again, you often want to do this to see, okay, how many distinct IP addresses am I dealing with right now, or how many distinct log entries am I dealing with, which I can do log. And so the question now is, can you count the number of distinct elements in a stream in less than linear time? Now again, this is easy to solve if you have buckets. You just maintain the counts, and you look at all the buckets that have a non-empty entry. All the buckets that are non-empty, that's the answer you want. But you can't do that because you don't have buckets. You're not allowed to. In which case, how could you do this? And this leads to a very clever algorithm, which again came up before we thought about streaming as a form phenomenon. The idea for this method I described to you came out in 1983. Well before people were thinking about streaming algorithms, which is a lesson about how sometimes, old papers are different, and, actually I have a lot of relevant tools that can help us right now. But this paper had a very cute trick that I want to share with you now as a way of showing how thinking about these very constrained models leads to all kinds of interesting ideas that tend to be useful in larger contexts. So this is a hard problem because we can't maintain the actual counts. There are too many of them. But someone want to maintain distinct elements. And here actually is where hashing turns out to be very helpful. So think of hashing all my elements to the line, to the continuous line. So I have, all the green elements go somewhere, all the blue elements go somewhere, all the red ones go somewhere else, all the orange ones go here, all the red ones go here. Right? So if I build a hash function in some form, a random hash function, all the ones will go one place, all the twos will go one place, and so on. Okay. Yeah. And so I hash them here. Here is now suppose I do this calculation. So let's say there's some function, I choose some function h of x, so I choose a random function h. Okay. And now what I do is, I compute y is equal to the min of h of x. Now notice this is very easy to do, right? As an element comes in, I hash it, record the value. if it's, you know, if it's bigger than, if it's smaller than my currently stored min, I just replace it. So I can do this very simply. With one sort of element of storage, I can do this computation. I need to store the hash function as well, so that takes a bit more storage. So this is easy to implement my stream. My element comes, I compute its value, I check if it's smaller than the current value, if so I replace, otherwise I throw it away and I go on. Now, H is chosen at random. Therefore, Y is a random variable. And now you can ask yourself, what is the behavior of Y? And so it turns out you can show and there's not a too hard a proof of this statement. Now I'll give you the notes to look at this. So basically a simple integration. But here's an intuitive argument for why this should be this. We're assuming that the hash value maps everything uniformly to the equal. So everything has an equal chance of being anywhere equal. Okay? So if I scatter k things in the unit interval, they should kind of sort of space out evenly. Because of the k things, and they're just being chosen randomly. There'll be some noise, but they're kind of spacing out evenly. If you imagine what an even spacing would look like with k things, this is the min value. How much is that? It's going to be 1 over k plus 1. If everything was perfectly even, which of course it's not. But when you do it randomly, and everything is uniformly likely to be anywhere, on average you will expect the min to be somewhere here. It might sort of move around, but on average it will be somewhere here. So the expected value of this, I mean, the way you actually prove it is you say, okay, what is to compute the expected value of y, you need to know what is the probability that y lies in the range from some t to t plus delta. Right? And once you have that function, you can integrate it. Well, the probability that y lies in this range is the probability that the min of all of them lies in that range, which is the probability that all of them are above that value. Right? The probability that all of them are above that value is something like, so the probability that all h of xi is greater than equal to t, right, is something like 1 minus t to the k. That's right. Just make sure I have that. No, sorry. Let me read this. The probability that y is greater than equal to t is the probability that all the hash values are more than t. And this is equal to 1 minus t to the k. Right? Because for each distinct value, it's only allowed to be in the range from t to 1 if this is going to be true. And so, once you have the cumulative distribution, which is this, the actual, so the probability that y is less than equal to t is equal to 1 minus t to the k. Then the probability that y is in the range from t to t plus dt is the derivative of this, which is something like k times 1 minus t to the k minus 1. And now you have to integrate this quantity. So I'll give you the notes, you can work this out, but you can do the calculation. But the intuition is that when you put these things down, you're going to get that much gap here. So why is that useful? That's useful because now if you imagine this random variable as the min of all the hash values, our algorithms basically do this hashing, get the min value, and take its reciprocal and subtract it. Right? That'll give us k. In expectation, what we will do will be correct. sense some misgivings in the book. So maybe I'll just stop for a second. I will reflect on this algorithm. So again, the algorithm is choose a random hash function that maps things in the range of 0 to 1 with some precision. Do this, run this hash function for every value, storing the minimum value you get. So that's a single stored unit. And then when you get that value returned, take its reciprocal and subtract 1 because we know that the expected value is 1 over 30. So any questions about the algorithm before I continue the discussion? Yeah. Oh, it's a random. It's a function. So think of a hash function. It's sort of a function that maps the domain to the range 0, 1, but it does it at random. So for example, one way you could do this would be to map U to some set of L bits and interpret the L bits as the binary representation of the number between 0 and 1. That's one way to think about it. But it's just some random hash. But it has to be chosen random. That's what it is. So we're randomly scattering elements. And the point of using the hash function is that all the elements that have the same value will go to the same place. Remember, our goal is to count the number of distinct elements. We don't care if 1 shows up 5 times. But the hash function we pick will send 1 to the same place over and over again. That's the function. So that in a calculation of the min, the fact that 1 showed up 10 times doesn't matter. It contributes to the min exactly because it exists, not because it existed 10 times. Right? And that's why the expected value only depends on the number of distinct items. It doesn't matter how frequent they are. Yeah.
And this t is one of the points between 0 and 1.
No, so this is for any, think of an arbitrary t. If you want to compute the expected value of y, you have to say, okay, what is the probability that y is equal to t? Now this is a continuous problem, so what you're simply saying is what is the probability that y is in the range of t to t plus delta t? Okay, for any t, then you integrate over t. Because these are all the different choices. So we're saying for any t, this is going to be the case. Because if you're saying that y is more than t, you're saying the minimum is more than t. That means you're saying every hash value is more than t. But if elements are being mapped uniformly to this range, the probability of it being from t to 1 is 1 minus t for one element. But there are k distinct elements, so the probability of this happening is 1 minus t. That's so if you want to say that the min of a set of numbers is at least 5, then every number must be at least 5. Well, what's the probability that every number is at least 5? It's the product of the probabilities that each individual number is at least 5. Each individual number is at least 5 with this probability. Well, 5.5. That's the argument, right? So this is the same min and max, right? If you want to show the max is something, the max is less than something, then everything has to be less than that. If you want to show the min is more than something, then everything has to be more than that. And that's what we're saying. So the probability, therefore, that it's not that the min is less than equal to t is the opposite of that. And this is just a standard transformation between cumulative distributions and actual probability density functions. Right? If you want to compute the probability density function for a continuous random variable, you compute its cumulative density and differentiate it. And that gives you the density function. And so that's where, so if you integrate this quantity here, you'll get the expected value one. You integrate technically this times t, right? So you have to integrate tk times 1 minus t with k minus 1. So we have a random variable now. We have what is called an estimator that estimates the quantity we're looking for, the number of distinct elements. But of course, as you probably remember by now, having an estimator is not good enough. You want to know how badly the estimator deviates from its mean value. If I ran this and I got some number, how do I know the number is reliable? I know on average, if I ran it a gazillion times, it's reasonable. But just doing once, it doesn't work. And to analyze that, we need things like a Markov count, or a Chebyshev count, or a Chernow count. Things like that. So you can do a Chebyshev analysis for this. You can find the variance of y. Okay? And you can say what is the probability that the y minus expected value of y, right, is more than epsilon times more than epsilon times epsilon over k plus 1. So how much is it? How much does it deviate from the true value? It turns out this is very bad. This is less than 1 over epsilon squared. This is a very bad estimator. Why do I say it's bad? Think of epsilon as being small. This number becomes useless. It's saying, oh, the probability is less than 200. Okay, but that doesn't make that is not very helpful, is it, right? So we have an estimator that in expectation is great, but has a very bad tail. It could vary a lot. What is the thing we're supposed to do then? If you have an estimator that's bad, but has good expected value. What can we do to such an estimator? What is the basic concept for such an estimator to make it work better? Yes?
Amplify.
So what does that kind of mean in your mind? I'm not in a specific case. In general, what is the idea here?
Run it multiple times.
Do it multiple times, do something over and over again, right? So you're getting a numerical value, right? The numerical value and expectation is good, but we know that it can vary a lot. If you run this multiple times, what should you do with this numerical value? Because you know its expected value is good. What would be a reasonable thing to try? So if I have a thing I'm running, and it's supposed to give me the answer between 0 and 1. First time gives me 0.2, then 0.3, then 0.7, 0.1, whatever. What should I do with these values as part of my amplification strategy to try and get a better answer? When I know that the expected value of this estimator is good. Take the averages, right? Because the expected value is the average. So if I'm saying I'm getting all these different values, on average this should be good, so let me take the average. So my next strategy is take the average of our estimators. Now, roughly speaking, and in this case this works, if you take the average of our estimators, the variance of the average will be essentially 1 over t times the original variance. So the variance goes down, right? And if you plug that into this Chebyshev inequality, the probability, so let's say z is equal to sigma yi divided by r. So there's I iterations of this estimator, and you just do this r. You can do them in parallel. You can do this in parallel r different hash functions, right? So you choose that much more memory. You can show that the probability that z minus the expected value of z, which is the same as expected value of y, is greater than or equal to epsilon over k plus 1. Will be less than something like 1 over r times epsilon squared. So the probability has gone down. Which means that if we choose r to be something like, I don't know, 3 over epsilon squared, then the probability is less than 1/3. But if we do this all in parallel, what we're saying is that if we use, remember, one of these estimators took constant memory storage. You just need to store a bin. Now I'm saying I can do all of these in parallel. But the number of estimators I need now is only this much. It only depends on the error term. So with the amount of memory that only relies on the error term, I can get an estimator of the number of distinct items, but the probability of being far away from the estimator of epsilon off is only 1/3. And now, of course, you can apply sort of more amplifications if you want, and you can do even more clever amplifications. Instead of taking more and more of these samples, take a few of these z samples and take the median. It turns out that works even better. And there are things you can do here. But the point is that to count the number of distinct elements, you need only 3 over epsilon squared units of space. And each unit of space is something like log n bits to record your record a number, because the number of distinct elements, log of m, sorry, because you need to count the number of distinct elements. And so you need something like log m over epsilon squared. So using just log m over epsilon squared bits, you can get an estimate of the number of distinct elements using this hash tree. So this is again a very counterintuitive idea. It's not something you'd expect to be able to do. But the streaming model forces you to think cleverly and come up with an answer like this. And so this whole area of streaming algorithms is a whole collection of things where you can use tricks like this For example, I can tell if a graph is connected. I have a streaming graph at Jagat, let's say Facebook's graph. I stream all the edges in. Computing connectivity is easy, and when you're done, you can store the whole graph, which obviously you can't. But in a stream, you can, using space that is very small, using more sophisticated versions of these ideas. And there's a whole literature around this now. So again, it's all what I want to sort of give you this lecture, a little taste of some of the new things that are happening in algorithm design. Well, we're 20 years old, but still ongoing and new, driven by the fact that we have these big data problems. And then by coming up with a model of computation that is maybe unrealistic, but captures what is it we want. So there's been a lot of cool ideas for how to do data reduction, data sampling, data compression, just based on thinking about the stream. All right, so like I said, on Friday, we will do review, and on Monday, so if you have questions about various parts of the syllabus, you should visit the site. We're going to talk about it. We also have a final assignment. It looks like there are 4 questions. It looks like it's long, but it's actually, I would think, a relatively simple assignment. You just have to apply the stuff we talked about in class, how to construct a linear program, how to construct a dual. It shouldn't require too much sort of thought. So hopefully you can finish it by next Monday, or next Tuesday. Okay. All right. I'll see you on Friday.